Because with special cases, we're going to be looking at difference of squares particularly today. So, let's take a look. We should have 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared, 36, 7 squared, 49, 8 squared, 64, 9 squared, 81, 10 squared, 100, 11 squared, 121, 12 squared, 144, 13 squared, 169, 14 squared, 196, 15 squared, 225, 16 squared, 256, right?
Yep.
Okay. 17 squared is? 18 squared? 19 squared? 361? And we have our 400 at the end. It's those last three we worked for me that I lose track of. Don't work with those enough to keep them memorized as much anymore. All right, so difference of squares. Being able to have this table that's going to help us as we go through the rest of this. Okay? Sure, we got that. All right. So the binomial expression a squared minus b squared is called a difference of two squares. It has a pattern to it. So you have a minus b times a plus b, or a plus b times a minus b. So what we call those are conjugates. So a term that you will see somewhat in this class, you would see it in Algebra 2 as well. So it's the factor and one subtraction, one addition. So difference of two squares, because it is a difference of two squared values. So x squared minus 81. First of all, you want to look for these. There's only two terms to it. There's subtraction in the middle. And we have x squared minus 9 squared. It can be written as a difference of two squared values, because 81 is 9 squared. So that means the first factor is x minus 9 multiplied by its conjugate, x plus 9. So number 2, 16n squared minus 25. Two terms, separated by difference. 16n squared can be written as 4n squared. 25 can be written as 5 squared. So I have a difference of two squared values. So that means the first factor, 4n minus 5, and its conjugate, 4n plus 5. So you have the exact same factor, one subtraction, one addition. So the last one, 16a squared minus 9b squared. Well, we already know 16 can be written as 4a squared. 9b squared can be written as 3b squared. So once again, difference of 2 squares. So 4a minus 3b, and then the other factor, 4a plus 3b. Again, that table at the top is going to come in handy, using that as a reference. What was the original value before it was squared? How are we doing on these? Pretty good? These should be the easiest things to factor. One of the easier ones compared to the trinomials. All right. So number 4. 49 is what squared? So I can write that as 7x squared. What's 36? So then I have 7x minus 6 and 7x plus 6. See if you can come up with number 5. So what did you have?
M squared minus 10 squared.
Perfect. So that means m minus 10 and m plus 10. I've had a couple people give me strange looks with number 6 because 72 and 50 are those squares. Okay, so, but can I divide both 72 and 50 by something? What? It's even, so we can always divide an even number by 2. Okay, let's try that. Let's factor 2 out of both of those. So that means I divided each of these by 2, which gave me 36p squared minus 25. Do I have perfect squares now with 36 and 25? Yes. So the 2 is just going to stay there, just along for the ride as we keep going. I'm going to use a different grouping symbol so I can see what I'm working with. I have 6p squared minus 5 squared. So again, the 2, just along for the ride. 6p minus 5, 6p plus 5. So sometimes you have to factor a GCF first to get the difference of squares. All right. So see what you can come up with for 7. It also is not a difference of squares. But can we do a GCF and get it there? When he gets back. So I could divide 2 and 98 by 2. And they both have an extra a. So then that's a squared minus 49b squared. And there's our difference of squares. Sometimes it works, sometimes it doesn't. Sometimes GCF is as much as you can do. So for the difference of squares, I have a squared minus 7b squared. So the 2a up front, a minus 7b, and a plus 7b. Now number 8, I would want to change the order. Instead of negative 81 plus a to the 4th, I would want to write that a to the 4th minus 81. Well, I know that 81 is 9 squared. And 8 to the 4th is a squared squared. There's our perfect square. 2 times 2, giving us the exponent of 4 from the beginning. So I'm going to have a squared minus 9 and a squared plus 9. Now only one of those is still a difference of squares again. So this one, not a difference of squares. So a squared minus 9. A squared minus 3 squared. So a minus 3, a plus 3, and the a squared plus 9 that was not a difference of squares. So in order for something to be factorable, it has to have rational roots. Rational zeros. So in other words, when I solve it, I can solve it. I get a real number out of it, okay? A squared plus 9 will not do that. It's not factorable at all. So just keep that in mind when you have them. There is no such thing as a sum of squares. Only a difference, okay? So what I want you to do is factor the trinomials at the top of the next page. So we have our A is 1, our B is negative 16, and our C is 64. So A times C is 64. B is negative 16. So multiplies to 64, adds to negative 16. So that's going to be a negative 8 times a negative 8. Since our A is 1, I can go directly to x minus 8 and x minus 8. Or I could write it once. With an exponent of 2 to tell me that there are two of the same thing. So these three are what we would consider special factors for trinomials because you get the exact same two factors. So we consider these perfect square trinomials. There are special ways to go about factoring them as a somewhat shortcut, but by the time you take the figure out it is a special trinomial, you could have just factored it the normal way faster. Okay, so I don't do anything different on these. So when we look at 10, we need 5 times 5 for 25 and 5 plus 5 for 10. Again, our A is 1, so I can go directly to my factors. 11 what will multiply to 100 and add to 40. Do we have anything? Probably because I had the wrong number up there. What if we changed our 40 to a 20? Because that's what it should be. Since I'm looking for the same two numbers, what does that? 10 and 10. So change the 40 to a 20, because I had the wrong number up there. So we have 25p squared plus 10p plus 10p plus 4. So now I can't use the shortcut because a is not 1. Out of the first two, I can divide those by 5p, leaving me with 5p plus 2. The second two, I can divide both of those by 2, leaving me with 5p plus 2. So I have the exact same two factors. When you're doing the x to figure out what those two numbers need to be, if you use the exact same two numbers, then you'll end up with the same two factors. Okay? All right. So solving. First of all, it needs to equal 0. So on 13, we need to subtract the 1. So it's 36n squared minus 1 equals 0. So on letter number 12, I can divide 2a cubed and 72a by what? They both can be divided by 2, and both terms have what? An a. So if I divide both of these by a, I now have a squared minus 36. And a squared and 36 are perfect squares. So I have a difference of perfect squares. I have the 2a in front and the a squared minus 6 squared. Which means a minus 6 and a plus 6. Every factor that has a variable we set equal to 0. So now, this time, we have to let 2a equal 0 as well. The first one, I divide both sides by 2. A is 0. On the second one, add 6 to both sides. A is 6. On the last one, subtract 6 from both sides. A is negative 6. So, negative 6, 0, and 6. A lot of times you will see this written with the negative and the positive 6 stacked, like that. If they're the same number, one positive, one negative, you'll see that happen. So this one has a difference of 2 squares. We know 36 is 6. 1 is 1 squared. So I have 6n minus 1 and 6n plus 1. Solve. We factored it. Now we need to solve. Finish solving that one. So 6n minus 1 equals 0. 6n plus 1 equals 0. You should, when you solve a difference of squares, get the exact same solution, one positive, one negative. So the first one, we're going to add 1 to both sides. Then when we divide by 6, we get the fraction 1/6. Here we're going to subtract 1 from both sides. Divide both sides by 6. N is a negative 1/6. So as I write my solution, I can either write them separate or I still have 2 answers there, but I can stack them because they're the exact same number. One positive, one negative. All right. So on 14 and 15, do those. And then we'll go to the homework. So our A is 1, our B is 4, our C is 4. So 1 times 4 is 4. It's got to add up to 4. So that would be 2 plus 2 and 2 times 2. Since A is 1, I can do x plus 2, x plus 2. Do I need to set both factors equal to 0? You certainly can, but you're going to get the exact same answer. You're solving the exact same equation. So all you need on this one is to set one of them equal to 0. When I subtract 2, there's our solution. You get a duplicate 0. Okay, a duplicate solution, so you don't have to write them both. So this one, same values that we'll be looking for. Our A is 4, our B is 4, and our C is 1. The only difference is we can't use our shortcut because A is not 1. We're using the exact same numbers, but this time we have to break it up in 4 terms. Look at 2 at a time. I can divide both of them by 2n, leaving me with 2n plus 1. The second group is already 2n plus 1, so I'm just going to factor a 1 so I know what I'm working with. So 2n plus 1 and a matching factor 2n plus 1. Set only one of those factors equal to 0. The 4 does not have a variable, so we don't set that equal to 0. So I just set 2n plus 1 equal to 0. Subtract the 1. Divide by 2. N is a negative 1/2. So again, only one solution because the other one is a duplicate. It's the exact same thing. So there's no reason to solve that or write both of them down. We are going to take